So last time there was an issue raised about scales due to Govindarajan because he was talking about cutoffs. Are they valid and don't things decoupled? And nowadays it is widely this kind of decoupling to write effective Lagrangians is widely used. And there is even a slogan about what is it? What the ultraviolet completeness of the theories and so on. I don't know how valid they are. And I want to start by giving a couple of counterexamples where it clearly does not work. So clearly it's simply not correct. So let me start by looking at what happens with the something that we use all the time.
But you say ultraviolet cutoff completely.
People say they will write integral Lagrangian and it should be asymptotic, ultraviolet complete. Which by
what does that mean?
I am not responsible for the slogan, but what they mean is that you add other terms and make it renormalizable. That's what they mean effectively. But it is a slogan, but because many
but by itself it is not normal.
Yeah, that's exactly the point. And they want to add extra terms, alleged extra terms at infinity at large energies and make it renormalizable, and they're happy.
And those terms arise only at high scale.
That is their claim. As I say, I'm quoting. I don't want to enter this kind of language. I want to show that this decoupling of scales fails in some significant ways that we are very familiar with. Yesterday I had a talk with Krishna, and I think he did not quite believe me. But anyway, no matter. The striking example I know, which I think I first heard from Gelman, is related to spin and statistics. You look at the proofs of, what kind of theories do you read which will insist on spin and statistics? The theories I know which insist on spin and statistics are relativistic quantum field theories, local quantum field theories, relativistic local quantum field theories. Can I get anything like, so if you start writing relativistic local quantum field theories, quantizing spin integral particles fields by anti-commutators, for example, then hell will break loose. I think in that case, you will find that the energy is not positive definite or something like that. The world will become unstable. I think that is my reflection. So, this spin statistics is like is overriding principle. Doesn't care what kind of quantum field theory you write. This relativistic local should have spin statistics. What happens in non-relativistic physics? After all, what is the energy scale involved in so what is the typical energy scales involved in quantum field theories? Let us say for electrons, you should have electron and positron pair production. So it is of the order of 1 MeV. The electron mass is 1/2 an MeV. The energy scale where relativistic effects will show up is 1 MeV. But in non-relativistic physics, the binding energies of typical molecules are of the order of electron volts. So there is a 6 order of magnitude difference between what happens in non-relativistic physics and relativistic physics. Nevertheless, if you decide that you will use Slater determinants to quantize spin zero particles in non-relativistic quantum field theories, nothing will go wrong. Experimentally, it will be totally wrong, but nothing will go wrong with spectrum. You get some new spectrum, you get a theory. What do you do with that theory? Yeah, I don't know, because it will not agree with experiments. That is a different issue. Yeah.
But if something is wrong.
So in the relativistic case, if you do this kind of activity, for example, the world will become unstable. Hamiltonian will not be bounded zero. It will fall down the hole. So there are And charge density, I think, from fermions, if you use commutator, I think charge density will not be well defined. Something happens. I'm not remembering the conditions, but something physically will be, something will be intrinsically wrong. You will not be able to proceed. Non-relative physics, so far as I know, nothing will happen. You can go on doing this. Okay? You can also put fractional statistics. We can do what you like. They may not agree with the experiments. That's a different issue. Okay. So there's 6 of, so in effect, which is happening at MeV scale is affecting physics in molecular physics, the order of electron volts, and it is affecting biology. Biological molecules are molecules, and their binding energies are the order of electron volts. And if you start describing the molecules by, say, some density functional method, but using the wrong unusual combinations, you will get totally wrong answers. Okay? So, what is happening? There is no decoupling. Yeah, they compute the electron molecular energy scales for large molecules, for example, by putting hundreds of electrons, and they put variations calculations. I don't know, these density function methods, I think thousands of variation parameters, because they want to get a very accurate answer. So they use it. That I know. Have they, anyone of them tried with the wrong steps? Reversing. So it take electrons use commutation relations and put electron wave function with commutations, what happens? They'll get some answer, but it will be totally wrong. Okay? And as Krishna pointed out, I can also show this by the fact that we don't fall through the ground. If the Pauli principle were not operative at macroscopic scales, we go right down this ground and I disappear. Okay? And all of you will disappear too. So I have accommodate you. So that's fine. No problem. Okay? So this is one example where there is no such decoupling. It seems to be an overriding principle of all quantum physics. It is spin statistics relation. Doesn't care what you do at relativistic physics, non-relativistic physics, you can't do anything. There is no decoupling. And if you do purely non-relativistic physics and you don't know anything about relativity, you would not know about it. You get into a big, complicated arguments, as Pauli did earlier when they were looking at Zeeman effect. So similar things will happen. Okay? So this is one example. Okay? I want to give one more example, then I'll go on. The second example goes to CPT. Okay? CPT is again, if you want to show a compelling argument for CPT, without which you cannot write a quantum field theory, you have to go to relativistic local quantum field theory. I know no relativistic local quantum field theory which does not respect CPT. Okay? Can I write down a theory without CPT? Yes. There are people who write down Lagrangians with all kinds of non-local CPT violating terms, and they keep going. But they are violating fundamental principles of physics. Okay? So, does the CPT decouple from low energy physics? The answer is no. I give you a simple example. You look at the decay of mu minus, look at the lifetime, and the decay of mu plus, look at the lifetime. CPT says they are exactly equal. Okay? And experimentally, we know that they are exactly equal. And also the angular distribution of the products are precisely the same. Okay? Well, except that the decaying products particles are replaced by antiparticles, but they are exactly the same. And so far as I know, this is experimentally confirmed. But so CPT also does not decouple. So where is the scale business? I don't know. Is there a scale involved? What is happening in that language? I do not know. So I just want to bring to your attention that there are loose ends to be tied up with all this business of ultraviolet completeness and stuff like that. Means not CPT. No, it just decay. It decays into mu minus goes into E minus nu bars. Yeah. You can say if you don't like it, I'm aware of it. So the equality of the particle and antiparticle lifetime, not the fact that you may be right, because I was also uneasy in writing this example, because you have to replace mu minus by mu plus. And the energy scale of mu minus is about 130 MeV, right? So you may object to this. Okay? So I was only looking at the rates for the particle and the antiparticle, which does not seem to be involving a scale. I may be wrong. So you can reject it if you don't like it. I am uneasy, but then you can take the first example. Okay? I have no problem with that. There must be other example. Okay? I cooked it up yesterday. So there must be other example as well. Okay? So, okay. So I also want to clean up what I did with Weil algebras, because this is the way towards proving all these results using this technology of Tomita Takesaki theory. How does it enter? So what yesterday I did, the notation that I was copying from these three people, Brunetti, Guido, and Longo, I think the notation is very bad. So let me start all over again. So what in those notes, there is something I call E0, and E0 is what we call the vacuum in standard quantum field theory. And let me write it in the JNS notation as a ket. So E0 is a vector in some Hilbert space.
Sorry, Bal, we can't see your slides.
You cannot see my slides.
No.
Somebody is complaining. Who is that?
Bala.
So, a slide department. So, I want to show that the Weil algebra representation they wrote down is really a JNS construction we do for coherent states. So, let me go systematically. So, what we start with is the vacuum state, which they call E0, but I write it as a ket vector. E0 the ket vector. Then they had fields. I wrote down fields, phi, scalar fields, Hermitian scalar fields for mass L, and integrated it over a test function which is compactly supported to some reason. Phi of L, and act on this E0, then this state I am getting by acting on by this operator on E0, I can label it by the function F. Because phi is fixed. So I can label this state by a function F. The function which I am indicating this object F. And F will be taken to be real. That is going to be important in the further calculation. If you do that, then you can see what is phi F times phi G. I know they create commutation relations of phi F and phi G. I can write down, notice the fact that annihilation operators annihilate the vacuum state and creation operators don't, and they have the standard commutative relations. You can see what it is, and this is the symmetrized product of FG. This FG plus GF up to a normalization constant. You can check it by hand, it's quite easy. But one very important thing to get the symmetrization is that this F and G are real. If it is a complex test functions, you won't get this. You'll get extra terms. And this is going to play a very important role when we go into the Tomita Takesaki field. So it's a small calculation. I checked it this morning also. And this answer you will not get the symmetrized product unless F and G are real. So that the scalar product I wrote down, S star G integrated, should be even under the complex conjugation. F star G should be equal to G star F. That condition is not fulfilled unless you have F and G there. That's an easy thing coming from the fact that the Fourier transforms for F, if it is real, the modes for K and minus K are related.
So phi of G will create a state G, right?
Because phi of G will create a state G.
Yeah. G. What is the actual annihilation operator corresponding to phi of L?
You have to phi of G, there is an annihilation creation operator.
The annihilation operator is the annihilator value.
Yes.
The creation operator will give you the get G state.
G.
Then you have an annihilation operator corresponding to phi.
So you move it through using the combination relations. So AQ dagger is delta function of K minus Q. Okay. But there is a smearing with G and F. Just work it out. And this will be something involving F and G. Okay. Everything else will disappear because of the fact that the vacuum is annihilated by the annihilation operators. Okay, so that's what happens. Okay. This is a simple enough calculation. It's not, this thing is not F plus G, it is something you can calculate quite easily. So how do I get the scalar product? So I am doing it for free fields without any Weil algebra. To get the scalar product, I just take this this object here, FF. How do I find it? I gave the formula, it is F. It is given by the what I call the Fourier transform, which is called F tilde, and F tilde star F tilde integrated over d cube k over 2k0. This object, how did I get it? You take phi f, phi star f for these two s, take their vacuum excitation value, do the calculation. So you will get the answer I wrote down. So the scalar product I wrote down between S is simply the standard scalar product of the Hilbert space transferred to test function. That's all what it is. This one is. So now let me go to the Weil algebra. If I the Weil algebra with test function f is the exponential of I times I over square root 2 times is 5. Okay. So that is a power series in 5. So I know what this state is because I know for each phi of f I know what the state is. So this is the coherent state of any number of particles, which I will label by putting W of f there. Okay. So W of f acting on 0 and part W of f times 0. Okay. And we know the scalar product because I know what the scalar product of 1 particle, 2 particle, 3 particles, and so forth from the previous calculation. And this is a symmetrized product. This is an infinite series where the number of operators, there are occupations for arbitrary number of particles. And the Hilbert space I get from here, from this W of f, is what they call as script H. Okay. The script H Hilbert space is with this scalar product. You have the scalar product to consider the Hilbert space, but it is different from the operators. Okay. So there is a distinction. Although the same kind of notation is used for vectors and operators, they are really different because at some point I have to take these vectors and take also limit points and complete it into a Hilbert. So when you do the completion, there are more vectors here than what is there in the operators. This is exactly the GNS construction that I am doing in the case of the Weil algebra. This is what they want to say, and this is what it is. It's quite simple, and I don't know why they discovered this bad notation. So you may ask, given this, okay, how do I act with some Weil operator? I need a representation of the Weil operators as operators on this Hilbert space. So what do? I say that W of G acting on a vector like this is a new vector where W is put inside multiplied W. Okay? And this is some function of G plus F times F place. So this is the action, and this action is compatible with the algebraic relations almost by construction. So they got now a representation of the Weil algebra in the case of a free electricity particle of mass m. The important thing here is if and G are real. So there's a reality condition W of f star W minus f, and this reality condition is going to be very important. Now what we want to recover next is to recover this algebra, forgetting about these f's, entirely from vectors of an abstract Hilbert space from spin 0, and in fact for any spin. And much later I will also do it for spin half. For Fermi case there is some little thing we have to do. For Bosonic case I'll get the whole thing. You don't care what the skill is, where it is coming from, I get the answer. So it's a very beautiful thing. And the power of the Tomita Takasaki theory is technical. Okay. Now I'm going to come to the crux of the matter. Okay. This is not at all obvious why it happens, but I'll show you how. Here, these are all last lectures contributors. Now I keep going. So I want now to start with what they call an abstract definition of the Weil algebra. Where is that? I have it a minute ago. Yeah, here it is. So they proceed to define, I think maybe it is known this way, for an abstract definition of Weil algebra. So I don't now I forget about all functions. Okay? And I have a Hilbert space. Okay? So what I want to do okay, is I want to pick this Hilbert space and I want to pick what they call a real subspace or the Hilbert space. But remember that Hilbert space is not functions. Okay? It's just abstract elements with scalar products. So what do I mean by real Hilbert space? And what that means is that in this subspace, only real linear combinations are allowed. Okay? If you take complex linear combinations, you go out of this real Hilbert space. So only real elements are allowed in taking linear. So it is a subspace which lets you take real linear combinations, but not complex linear combinations. I'll tell you what, for example, the functions f, which we call as real, means for the functions, I cannot take complex linear combinations because that is not allowed there. Okay? This fact will be reflected more abstractly here. Okay? So I take a real subspace okay? And for each h that I write down the Weil algebra WH. What is the WH? All that I need to know about WH are two relations. One is the defining relation, that WH times H1 times H2 is WH1 plus H2 times minus expression of minus I over 2, that is the imaginary part of the scalar product of H1 plus H1 H2. That is my definition of the Weil algebra. For the real subspace of H of the complex Hilbert space, and tell you how to put the real Hilbert space. It must fulfill one more relation which you wrote down. The WH, there is a star operation, this algebra, which is the Hermitian conjugation when you finish the calculation. And W star of H to be W minus H. We found that from real function. We want this relation. If you give me this and that, then I can construct the Hilbert space by what I did earlier. So I take vectors, vacuum vectors, and in the vacuum vectors, already I know from the case of the real scalar field, what is the scalar product of two vectors labeled by f and g. I just pick that. It's given in terms of scalar products. Just pick that and write down the corresponding Hilbert space here, and that gives me a Hilbert space representation of the Weil algebra abstractly defined. You may ask what is the use of this abstract definition, and that's where the surprise comes to you. At least came to me. So how do I pick this real surface? This real surface is picked by picking an anti-linear involution, which in specific cases has a meaning. For example, for the Miller wedge, you will be able to write it down explicitly. Some anti-linear involution. Involution means the operator s squares to 1. Okay. It's not unitary, okay, but it is involution. Okay. So s squared is 1. It's anti-linear. So in linear combinations of vectors, it complex conjugates the coefficients. because of anti-linearity. And I take this operator, look at the Hilbert space, and look at all vectors that are invariant by this S. Okay. In the case we have considered previously, sorry, vacuum will be an example where which is invariant by S. Okay. But now we are picking a whole subspace of the full Hilbert space, and it could have, and we'll be able to pick it. Okay. It's an infinite-dimensional space, we will be able to pick it. So they will correspond in terms of functions to all real functions. But abstractly, we don't need it. Just have this equation. And there is one more relation that if you take the real part of H, so real part of H is this real subspace plus I times the real part of H is a imaginary part, and you take the direct sum that creates for you, after closure of course, the full Hilbert space. So you are able to decompose the Hilbert space into a real and imaginary part in a colloquial way. You can't say that small h in the Hilbert space is real. There is no meaning to that. Okay? Just like time reversal is anti-linear, but you cannot say some vector is real under time reversal. It doesn't make any sense. Okay? Because time reversal is a notion of complex functions in a Hilbert space doesn't make much sense. But this makes sense. So you want the real part of H and I times imaginary real part of H, and the intersection will be only the okay? So together they generate the entire Hilbert space. This happens, then one shows that this S, for example, in the vacuum state, E0 wrote down, that thing is cyclically separated. Okay? So you can go ahead and this S is a good Tomita-Sakazaki operator, and this way of writing it is called the real form of the Tomita-Sakazaki. And you will see that it plays a very crucial role for the development. Okay. So what do I do? The one thing you should do is that once you give me S, once you give me this S, and I take any vector in the Hilbert space, abstractly given, could be harmonic oscillator objects, or it could be something else. Then I can split it into two parts. One living in the real Hilbert space. What do I do? I take 1/2 of 1 times 1 plus S, actually on ether. Then I take what I call imaginary part of it. Yeah? The IO2 times 1 minus S on ether. And I add and the S, this will not change because S squared is 1. And the rest will change inside because of the fact that you have 1 minus S here. So get S minus 1 changes the term here. So this is the real part and the imaginary part. So and the entire theta, you can write this sum of the standard way, the real part of theta plus I times imaginary part. So I do that. So I have got this Tomita operator. This will be the Tomita operator. Now I have to ask, what do you do with this in quantum field theory? So my first step, and by the way, I have now somehow shifted away from ordinary functions to some Hilbert space representation. We will see that the Hilbert space representation I choose can be for particles of arbitrary spin and mass. It can be photons, it can be continuous spins, what they call continuous spins with infinite number of polarizations. Could be massive particles of any spin whatsoever, doesn't matter. We will be able to construct a full quantum theory and the Fock space for these objects. And I'll show you how that fulfills causality. Please ask me questions. I suspect that by now I have confused people, so you can ask me this. No problem. Now, having given this, I need some conditions on localization because I want to say yes. It will come in a minute from representations given by Hilbert by Wigner. So for a particular spin S and mass M, he has given a representation of the Poincare group on a Hilbert space. Okay. So that will be a typical example of this Hilbert space.
The last class, whatever we are talking about functions,
Yes.
Space.
Ah,
And that Hilbert space is what we are talking about.
yes.
And then now you're saying that that Hilbert space in some corresponds to the physical states that we talked about in one.
Yeah. So there should be a correspondence between what we talked about the functions, what is happening here. So what will happen is that this slide will show that this picking of the subspaces here will the speaking of the subspaces there were depending on localization regions. Here, the picking of the subspaces don't be like that. It will be a labeling set of the Hilbert space. Okay. It will be what a causally complete region of the Minkowski space, which I'll come to in a minute. So there will be simply labeling of subspaces of this big Hilbert space. So let me again say, there's only one Hilbert space. For all of all things, there's only one. Hilbert space is a giant object. So it can accommodate all of this and also us to no difference. It's huge. These infinite dimensional Hilbert spaces are in some ways the most frightening objects one can imagine because they can accommodate every damn thing. Okay? We may think that they are functions, they are not. So all these things will be put inside. So we go on picking real surfaces with different Tomita operators. So there will be a whole lot of Tomita operators depending upon the labeling W, which has to fulfill some Poincare invariance properties, Poincare covariance properties. It will pick subspaces, and for each of them, I will write this Weil algebra. Then I will show you that the Weil algebra with labels which correspond to causally cost-like, but the two regions which are space-like commute. Okay. It won't take any functions or anything. We'll just use these Tomita operators and get the answer. Okay. I will show you again that the vacuum state E0, which we wrote down, which is the cyclic separating vacuum from the right, induces always a KMS state, always on the local algebra. So Ungru says that the algebra on the Ungru wedge is thermal. It is nothing to these people because it is obvious. It comes right from the very beginning of the whole calculation, and it only takes two lines. You will see how it happens. It is coming purely from the and these properties of S, and which we will explore further. Okay. So at this point, I'm taking the functions picture and transferring it to some deeper space. So what do we need for localization region? Yeah. So as I said earlier, I will now associate real subspaces to localized regions. Real subspaces, they're not functions, they are just something. Yeah. But they will obey some Tomita operator coming from this labeling, that labeling I will do. Okay. So what is the labeling? The labeling will be given by this wedge region. So some of the wedge regions are basic, so they will come from this wedge region. Okay. So suppose I have a labeling region K, not here I can use the language K. We want this K, so there is a space-time region. We want this to have causality requirements. So what is it? It has to be causally complete. What does it mean? So, if you take all causal curves you write within any 2 points inside this K, should stay within K. This is what it means. So how do I get it? You take K, take all space-time points space-like to K, call it K prime. Take one more complement. So you take K double prime, And K double prime is what they call causally complete. And we want this K to be equal to K double prime. So that will be causally complete. That means no causal curve will escape that region. If you have 2 points in the region and you draw a causal curve, time-like curve, it will stay in that region. That's all. That is all this means. And an actual proof that this is what is happening is actually given in Hans' book. So to K, I will associate a wide algebra, which I will call WK. Okay. So K is a causally complete region, and I will call WK as I will associate it. So K will be a labeling. The algebra will be some set of operations in the inverse space. Algebra doesn't a priori know the where it is coming from, but I can use it as a labeling set. So I have got a K here. Causal diamond is some simple example. Rindler wedge is another simple example. But now you see that I can do much more complicated things. For example, I can take two causal diamonds or n causal diamonds and intersect them. Suppose I intersect them. The common intersection region is also a K. And their geometry, how they look like, can be very complicated. Okay? And these people, there is a whole, in more difficult papers, there's a whole appendix on Lorentz geometry, okay, which I have not studied. Okay. In Lorentz geometry, how does causality look like? There's a whole discussion. Okay. I confess that Fuster and Birch paper, for example, I have not studied it because that one needs patience, and I thought that I can avoid studying it. Okay. You need to sit and do it several days, which I did not do. So I write the index sequence is causally complete region, they call W. And I also want some Poincare covariance of this indexing set. What do I do? The Poincare group, which I will consider, will be what we call as P plus. So P plus are 4x4 matrices with determinant +1. It is not connected because it also involves CPT, namely the which are called R, and it reverses all the coordinates. Inverse rotations and unit has been mentioned, but also it involves the operation of reversing all the coordinates geometrically. So, in the quantum theory, I want a unitary representation of the Poincare group in the full Hilbert space. I'm not worried about finding a representation in each of these cases or anything. I'm talking about the standard Wigner representation on all of space-time. This is talk about space-time at all. I just want a representation of this Poincare group on the infinite dimensional separable Hilbert space, on which all operators are at. Any space-time region, including infinity, scattering theory operators, everything else. So on that Wigner representation X. So I want a unitary representation, unitary image of the element of G in P plus there. So I call it G, rho G. So rho is the representation which maps G to a rho G, which is the unitary operator of the Hilbert space. And I want the requirement that when I conjugate WK with rho G, it becomes the W associated to J times K, G times K. K is some causally complete region, so I know what G times K is. You would take K, move it by this Lorentz transformation, it will become some other region, which I call GK, and that also I associated with W. So I call that WGK. So the conjugation of WK should go into WGK. Okay. This is how we will incorporate Poincare invariance, Poincare covariance, okay. And yeah. So, but notice that this action here, when I take this total reflection like this rho of R will be G equal to R, it will be anti-unitary because it is CPT. Okay. So these anti-unitary operators are important. We'll come and see how that happens. And I also want to incorporate causality. So how do I do causality? I take WK, the algebra associated with K. I take the causal complement of K, it's a space-time region. I know what is a causal complement. All the region where everything is space-like to K. And look at the algebra there, WK, right? Then I need the requirement that the operators in WK prime commutes with the operators in WK. Okay? And that is the requirement of causality. But I notice that W's are not functions, they are operators. But I want them to compute. And there's something called half duality, which is stronger than this. This is that the algebra in K prime, W K prime, is the combination of algebra in K, in W prime of K. So this is half duality, where W K prime is W prime of K. Sometimes this condition is not fulfilled, but never mind. In many cases, it is. So we can assume this for the purpose of this set of talks that the half duality is also correct. And there is something called isotronic, which is more technical. You may ask, why am I putting a condition like this? Namely, if you take a subregion of K1 of K2, you take a causal diamond, take a smaller causal diamond, then what they call isotronic, then the algebra W of K1, the smaller region, is contained in the algebra of WK. We may think it is obvious, but mathematically it is not obvious. So we have to assume this condition also. So this is called isotronic, and physically it is very similar. Sorry, K1, WK1, we don't know that. That's a problem. If you take a sub-region and construct this W from the Tomita operator, so WK1 will be computed with its Tomita operator. WK2 will be computed with its Tomita operator. How do I know that one is subspace of the other? We don't know, because we don't know how the Tomita operators are related. Okay. In fact, we shall see very soon that the Riddler wedge boost, how it generalizes to all the case, is simply not known. We know it exists, but we can't write it. The only
I do appreciate, but the boost operator, the volume operator, any causal completely.
no, there is no booster operator in the causal diamond. It is true in the Riddler wedge, because you have constantly accelerated particles which can go through it. But there is no such thing in causal diamond. So, poor Longo did a long calculation that for conformally invariant theories, say Maxwell theory, he actually conformally transformed the Riddler wedge into a causal diamond, took the operators and mapped them, then checked painfully that the operators fulfill all the correct relations. But what he writes down for the S operator and so on, what they mean, nobody knows. I don't know. The answers are given in Hart's book, but if I look at it, I don't know what they mean. The general case simply not known. I'll come back to that.
This is true in the subset. W1.
Yeah, this is the isotronic. Isotronic is this relation. Okay. So I want to construct this WK. The starting construction in all these calculations, actually for power review, is a Riddler wedge. From the Riddler wedge, by general theorems, you can construct all causally complete regions in a way which I will explain. This is a property of Lorentzian geometry, which as I told you, I don't know, I don't have a good grip on that. So take the Riddler wedge. So the wedge I will take it will be in the one time one plane. So I don't do anything to do anything. So the Riddler wedge is second of all that will be my starting W, and I'll take all x in M4 encode the Minkowski space such that the spatial coordinate x1 is larger than the modulus of the time coordinate. So x1 is larger than x0. So I take this. So you can see immediately that this condition gives you the right wedge. X1 is larger, so you get the wedge where the P is pointing to the right in the 1, 0 plane. 2 and 3, I don't do anything. So I take this thing. Now, this plane has a particular property, which is very commonly used by people doing this. People doing quadron plasma or this collisions, so very high energy particles. Namely, in this plane, we can make Lorentz transformations in the 0, 1 plane. So the Lorentz, these are the, I don't know, there's a word that is used. So these are the Lorentz transformations in the constant velocity, which can be written as a 2 by 2 matrix, because it's only acting on 0 and 1, and it is this. So the Lorentz transformation as a function of a parameter tau is given, or t is given by this. T is not time, it is just a parameter of the group. Doesn't do anything to plane. This acts in this plane because it transforms x0, x1 within this plane, maintaining this relation. And furthermore, this action, it leaves W invariant, but there is another important property. In this whole calculation, I told you I have a CPT. Okay. So CPT will reverse all the signs of the coordinates. So let me take the new operator where I take all the coordinates and call that operator small JW, which reverses only the first two coordinates and doesn't do anything to the last parts. So what do I have to do? I first apply reverse all the coordinates, then do a pi rotation around the one axis. So I need so this operator here is CPT, which I call what I call R is this operator followed by a pi rotation around the one axis. So the 2, 3 axis get reversed. So that is brought back here. Okay. So I will then take the right wedge of left to the left wedge. So this operator JW will take me from the right wedge to the left wedge and vice versa. JW squared is 1. Small W squared is 1. Okay. So the properties of this operator is that it commutes with boost. There is boost in the 1, 0, 1 plane. You act with the 0, 1 plane for some time and apply this JW because this JW is acting like -1 in the 1, 2 slot. It simply commutes and goes right. So this is an important property. Why is it important? In Wigner representation theory, the geometrical operations you do in space-time become unitary operators in the Hilbert space. That is the fundamental rule. You take any geometrical operation in space-time, and when you convert it to an operator in the Hilbert space, the geometrical relations are maintained. What does it mean? It means that if I take rho, if I write this, how will it go? So I want to, so I have this relation, and I want to represent this small JW by a capital operator JW on the Hilbert space, that will consist of my theta, this is the CPT operation, and this pi rotation. The representation of rho by pi rotation, but notice that this theta is anti-limited. So rho. Now, meanwhile, if I take the representation of lambda WT, so this is the Lorentz transformation I wrote down the last transparency. this this 4 by 4 matrix, row of this is some operator in the given space. So let me write down. I have a unitary representation, so there is some operator. What is that operator? We write in the usual way as rho or lambda w is expression IT times the boost operator KW. Okay. So KW is the boost in the 0, 1 frame. This is what the representation of this operator is in the Hilbert space. The KW is the boost operator. And correspondingly, the small jw, which corresponds to transforming the right wedge to the left wedge geometrically, is represented by an anti-unitary operator. It's called capital JW, and it is a combination of CPT times the pi rotation. So, what do you do next? The geometry demands to you that since small jw commutes with going from commutes with the operation corresponding to geometrical operation here, the operator JW should also commute. Okay. This is very important because there is an I here. This is simply a expression of the geometrical requirement that what I do geometrically is maintained in the quantum theory, this equation. But the I fools you because J is anti-unitary. So when I pull it through, say multiplied by JW, you'll find that this I becomes minus I. So you find that this JW anti-commutes with K. Not commute, but anti-commutes with K. So the nature of K under this JW completely changes. It changes the sign of K. This is absolutely crucial, okay? And is going to play a very big role as you keep going. And furthermore, again for reasons of geometry, I will require that I have the Tomita operators in W and W prime. Okay. I don't know what they are. I find it, but it should fulfill the covariance property. So if I conjugate SW with JW, it should be JW squared is 1. So inverse is the same. It should give me the W S of W prime. Okay. So the Tomita operator with the right wedge and the left wedge are connected by this conjugate JW, which is an expression of CPT times the pi rotation in quantum theory. So this is again a nice geometrical experiment. I put that. Given all this, you are challenged to find S. So I go back to expression minus pi KW. KW is coming from here. It's a boost in the W plane. And let me look at explanation minus pi KW, which I call delta W to the power of half. You may immediately ask, how come I make T complex? Because it is plus IT, here it is minus pi. So what happens to T? I have gone into the complex plane, things are okay, I do that. In fact, they are okay, and there's a proof. So there's a proof, I think, already. Definitely in Cohn's work there is a proof, but I think Hart's book also has a proof, but it is not trivial. So I will simply accept it. So this object here can be continued. In fact, what they prove is that this expression for real T is a boundary value of a holomorphic function, which is holomorphic in a strip in the complex time plane up to this T plus I pi. So you take the boundary value, get what you started. What happens at the other boundary in 2 plus 1 is very interesting. It produces the conformal field theory in the 1 plus space time. Okay. So one boundary is a conformal. You can call it holographic. They don't call it, they just do it. Okay. And it is known to be a conformal field. So in general, I don't know what it is, but it exists. This.
Say that there are no boost operators in the local W is a complete then what does it mean to call KW the boost operator?
KW, no. W is at this moment not it's just the Riddler range at this moment. If you take causal diamonds, I don't know what this KW is. That is the issue. I'll come to that in a minute.
The W is right.
Right. I'll come to your question in a minute. Okay. So this expression exists, and normally it is called as a square root of some operator delta W. Notice that this operator delta W to the power of half has the property. Okay. So what is the Tomita operator? The Tomita operator in this case is simply JW, which is an expression of CPT times phi rotation times delta W to the power of half. That's it. For the inlet base. Now this is equal to, because JW reverses K, this equation is the same as this. Okay. It reverses K, so it becomes plus 5KW, so we get this equation. Okay. So we can compute what is SW. Notice that this what happens to SW. The two J's cancel out. What do you do? Yeah. So I'm taking this expression and multiplying it by this one. The two delta, the delta to the power half, delta to the power minus half cancel. I get JW square, but that is 1. So you find that SW is 1. Okay. So this is an anti-linear equilibrium. I have got an anti-linear equilibrium. But it is not anti-unitary. A very important point.
Equation 5 comes to consider definition. This is derived from some definition.
There is some other theorem which I don't, that this Tomita operator, if you take two Tomita operators, there is some unitary equivalence between them. Okay? There is some cone cocycle homology, and they prove that the equivalent. So pick one, you can be happy. Okay? If you find non-trivial cocycles in the cohomology of these operators, it is this Hochschild cohomology. Then you are changing the Hilbert's, changing the representation of the algebra. So you go to some super selection sector. Okay. So they prove it. Okay. No, I will not try to prove it here. Okay.
This equation is coming from that.
Yes. No, I pick SW.
Yeah, this is a definition of SW. Yeah. It's a product of JW and delta.
Yes. Yeah. It fulfills all the correct properties. I can keep going. Okay. So I got the SW. So what I have to do? I am still in the relay range. Okay. One important point is this K I am writing, this SW K. People say that it is a modular Hamiltonian. It's a terrible word because this K is bounded neither above nor below. It is not cannot be a Hamiltonian. It is not a bounded of, it is bounded neither above nor above. So you get infinite positive energies and infinite negative energies. And if you quantize it, the world will disappear in no time at all. If you literally take it as an operator giving energy, the world will disappear.
The energy is not the literal modular.
So
And they are not quantized.
putting in modular was safe. But if you go back to the early literature, they were using it literally as an Hamiltonian for the real limits. And they were finding eigenfunctions of this K and doing this and that. Hmm? This is lost in the mists of antiquity. Long ago, when Ritter first wrote his paper, there was a bunch of papers, and they were trying to find Hawking radiation from here. So, I don't remember, but I do remember seeing this paper until Sewell came along and proved that this is nothing but the this Tomita theory and connected to this activity of dissonant movement. I'll show you that also, and then I will stop. So I pick the real subspace of the Hilbert space. I say that all vectors in this Hilbert space are real if it is invariant by SW. In particular, the vacuum vector is invariant. And since this SW simple space carries a representation of all operators in the theory, it also has a vacuum vector. So the vacuum vector is invariant by this. And the claim is there is an infinite number of set vectors. So you are generalizing the vacuum vector to a whole lot of things, whole subspace of vectors. And it SW produces this relation. Notice that SW in the conjugate space is you have to take SW and conjugate it with J, so it becomes minus R. So vectors in the just right place will be invariant by this SW. Vectors in the left place will be invariant and this U SW given here. So the two SWs it stabilizes the subspaces are different, okay? But not very different because delta W is delta W to the power of minus R. That's all. Okay?
You're saying that there are infinite many filter.
Hmm?
There are infinite many vacuums. What did you say?
The vacuum vector is invariant by both. Because the
You had a formula operator SW corresponding to the right bits.
hmm.
And for that operator, there is a unique state that will remain invariant until the action.
I didn't say that.
But
But
I'm asking.
no. For subspace of vectors, which are invariant by them. There's a real subspace.
But there is one dimension.
No, infinite dimension. But take that subspace and add it by I times that subspace. That will give me the entire universe.
So I'm talking about only the real universe. The real universe is a unique state which is fixed by the
No, any vector in the real space is fixed by the without. Like the vacuum. So there are infinitely many objects in the real subspace, any of which you can use as cyclic and separate. Normally we use a standard vacuum, but you can choose any one of these vectors. I think you can even write them down. Okay. I have not done it, but I think these people have done that paper you gave me. Okay. So yes, there are infinitely many vectors in the problem. Okay. So now I have to show you, and that will be my last topic there, that there are two wide algebras, one from W and the other coming from W prime coming. So I want to show that the wide algebra in W prime is the commutant of the wide algebra in the original space. Okay. The prime denotes commutant. So what does it mean? Remember the algebra. The algebra I'm getting is multiply wide element W, we get W, and the psi W is multiplied. This W of eta plus I times the phase expression I over 2 times imaginary part of scalar product of NW prime, NW prime times psi W. Okay. There's a phase. So this thing compute, this phase has to be 0. Which means that this object here, this scalar product has to be real. Okay. This is what I emphasize. For functions, two real functions, you take the scalar product, the norm I gave, in the Fourier transform space, you check that it is real. Here I have to prove that, but I don't have a function. How do I prove it? And I think the proof is a very good example of the kind of manipulation we do. Remember that JW is anti-unitary. Okay. So if I take two vectors, alpha and beta, and I apply JW and JW here, is anti-unitary. So this expression here, linear is beta, but because of the J is anti-linear, they get vector. So whatever I did here, beta should go into a bracket by anti-linear. Likewise, this alpha anti-linear a priori, but because of the J becomes linear, so you go on the get vector. So and J is unitary. So the unitarity of a of a anti-linear operator is given by statement that this scalar product is beta times alpha. There is a reversal. Finger coordinate reading from left to right, left to right, or right to left in the correlation function. So there is a reversal. It's coming from the simplified. So let me do that. So let me see what happens if I take the scalar product of eta w prime inside of it. I want to show this is real. Okay. We know that this eta w prime is by the Tomita operator, SW prime. Psi w is very by its SW. Okay. So let me write down this SW prime, this JW times. And not seeing the JW times, yes, SW prime was JW times W, then delta W minus half. So it was on the right, then left, when I pulled it on this side, in the minus half, quite important. And here I get the standard Tomita prime. By anti-unitarity, the two J's cancel, but I have to reverse the signs. So this goes on the other side. So I get delta W, system here goes here, system here goes here. But delta W is unitary, is self-adjoint. So I can take this operator and put it here. And this is cancel. Because one is the inverse of the other. So this is equal to psi W eta W prime. So I proved to you that eta W prime psi W is psi W eta W prime. So I proved to you that this scalar product is real. We will ever appeal it to any function. So it is real means that I have proved to you that I have fulfilled causality requirement using this Tomita operator. And you will notice and appreciate that I have not used any functions to prove this. Okay? I just used the properties of the Tomita operator. Okay? Yeah. So it is purely intrinsic. So the notion of a real substance, the real form of Tomita Takizaki incorporates causality constraints of quantum field theory. And this construction I have given you, without any change, will go through for any mass and spin in the beginner list. Because I have only used Hilbert space properties. So it will go through for any mass and spin in the beginner list. Okay. So I stop here. And I'll say next time more on this Tomita operator. How you get other causal wedges and what is their characteristic. Then I will go on to prove the KMS property of all these causally complete regions and what happens to spin half. There is some twist, something new happens with spin half. I will talk about it. Then we will go to more on locality. If there are questions, I'll try to answer. You can ask. So anybody can hear.
I just take the right place of the window and I consider the window operated there. What is this? Can you give me at least two or three examples of the states that will remain unchanged after that? I know only the thermodynamic numbers, but what else to take?
You're asking me what is the operator? What are the operators?
What are the states?
What are the states? Okay. Okay. So one way for real scale for a scalar field is take a real function, take its Fourier transform for a real function. So it is in terms of creation and relation operators, some coefficients. Act on the vacuum, you get a vector. That's an example. It will be invariant. And that's because the modes of positive k and negative k are modes of negative k for a real function are the complex conjugates of the modes for real positive k. If the k is a momentum. Because of this fact, you can easily check that the Tomita operator is invariant.
These are all states related to scalar multiplication.
If you the scalar multiples are only real scalar multiples.
They are in the one dimensional space, that is
If you start multiplying them with complex numbers, then you go out of the real vector space.
But what I'm saying is that the way you mentioned, I can all the states are equivalent. They are
Yeah, they are equivalent for the Tobita, for the JNS construction.
Yeah, but I'm asking you distinct states which are the same under the SW. You said that there are independent distinct states. Right? I'm not asking states that are related by scalar multiplication. That is really-
Oh, you're asking other things which will do the same job.
For example, the thermophile double. Thermophile double.
Hmm.
That is very interaction with the light to the object. What other state that is not the thermophile double or a multiple of thermophile double will do the same?
So let me go slowly. Thermophile double is just a trick. Okay? So let me go back. Suppose I take WF. Now, suppose that is a unitary operator, and I have started from F's being square integrable. That is, now I am vicious minded. I take an F which is not square integrable, but smooth. I can do that. And I do this concept. So I start with the state where WF, it gets WF, where F is, I'm not clear on functions, but it is not square integrable. Suppose I do that. You can do this construction all over because WF is unitary. Scalar product will be defined. But it will not be in this Hilbert space. So what is it? It will generate by acting, using it as a cyclic state, you get another representation of this algebra, which is in a different supersession sector. So by choosing this different WF as a starting point, where F is no longer in the element of the Hilbert space I wrote down at the beginning, which you can do, you will get different supersession sectors. And physically, it happens, for example, because of infrared effects in QED. Okay. In fact, Probstov, in an impressive paper, proved that they all break Lorentz invariance. Proved. Okay. Is there anything physically wrong? No. He produces these state cells, infrared clouds. Okay. This is coming from some charged particles. And what do they do? What use? It happens that the Poincare group, Lorentz group is broken. The Lorentz group cannot be implemented as a unitary operator. He proved. Same thing happens with QCD, which I proved. Okay. So that's an example, I think, of the kind of question you're asking. What are the possible cyclic separating states? I think that's what you're asking. There's a whole lot of them. It is no.
For the same Tomito.
Tomito, the operator is any splitting of the Hilbert space you got into real and imaginary parts with the properties that shown. So in each sector, the Tomito operator will change. There is no unique Tomito operator. Nobody told that. So when I talked about entropic ambiguity, already we showed that there are many J operators. That is a kind of ambiguity in the definition of S. Okay. But in that case, it is sort of trivial. They are all unitary equivalent. But if I do the kind of thing I told you now, these operators you get are not even. So you have many CPT operators. That's what it says. The CPT operator changes from infrared sector to infrared sector. Which there must be physical consequences of this statement. And yes, I think that these issues of the consequences of Lorentz breaking experimentally are wide open. I think.